Okay, so just a couple of review problems, 3 review problems, and then I'll talk about the chapter 18 versus the chapter 19 test. This mixture. So if I gave you a diagram like this, and we said that these would be the partial pressures and the volumes before you open up the valve. Once you open up the valve and mix, instead of having 3 separate containers, you now have essentially created one big container, and the gases will diffuse and spread out and fill the entire assembly. So now they don't mention the little valve. Assume the valve is volumeless, that they've included it. So we're going to open up the valve and we're going to wind up with a new 1 liter plus 1 liter plus 0.5, 2.5 liter container. And they would say, well, what is the partial pressure? I'm sorry, what is the total pressure after mixing? So go ahead and try it. It's exactly the same as the one that I gave you as an example in the other videos. And then I'll pause and come back and show you how to do it. Hey, I'm done waiting. You've paused. All right, so what do we do? First thing we have to do is we have to adjust the partial pressure of each gas. So as soon as we open up the valve, the partial pressure of nitrogen is no longer going to be 265 torr. It's going to drop. So we have to calculate how much it drops. And we use Boyle's law in order to do that. So we need a new partial pressure. So we solve for P2, and then we substitute in. The original pressure is 265 torr, and the original volume was only 1 liter. But the new volume is going to be all the containers combined, 2.5 liters. So our new partial pressure is 265 times 1 divided by 2.5. And that gives us 106 torr. And now we're going to do the same thing, except that we're going to do it by analogy. And we'll do it for neon and for hydrogen. Okay, so first neon. So new partial pressure of neon. We don't have to rewrite any of the equations. We can just substitute in. 800 torr. Let's assume it was 3 sig figs. So I'm going to put a little bar over the 0 to assume, again, that they were talking about 3 sig figs. I'm limited in the pictures that I steal from the internet. And our new container is now 2.5 liters. So again, we do 800 divided by 2.5, and we get 320 torr. I'm going to put a little bar over the 0 to remind me that that 0 is actually significant. And then let's do partial pressure of hydrogen up here, so I don't have to scroll down. And that's going to be 532 torr. Original container is 0.5, but let's assume 2 sig figs here, because the other containers were 2 sig figs. And then let's convert that to the new container, which is 2.5 liters. So 532 times 0.5 divided by 2.5. And we get 106.4, so also 106 torr. All right, so now we can add them up. P total is going to be the new pressure of the nitrogen plus the new pressure of the neon plus the new pressure of the hydrogen, which is going to equal 106 torr plus 320 torr plus another 106 torr. So when we add that up, we get what? 212 plus 320, so 532. Okay. Second problem. One of those Daltons collecting a gas, and they're asking you about the dry volume. All right, so we said that when we collect gas in the lab, we use water displacement, and the water, some of it evaporates to create the vapor pressure at that temperature. So you really, when you're collecting the gas, you're not really collecting that volume. It's not just the gas, it's also the water vapor. So we're really dealing with a Dalton's law problem where our measured pressure is really the pressure of our dry gas plus the pressure of the water vapor. So the first thing I'm going to do is I'm going to adjust for the pressure of the dry gas, which is going to be the manometer reading minus the vapor pressure. So the manometer was 103.64 kilopascal. Oh, I'm sorry. Oh, you're supposed to pause, go back, try the problem yourself, and then come back and take a look at what I'm doing. All right, so pause. Okay, we're back. Minus 21.60 kilopascal. And that's going to give me, what, 82.04 kilopascal is actually the dry gas. From there, they want us to convert it to STP. So anytime we're converting to STP, we're changing the temperature, we're changing the pressure. They want a new volume. So we're going to have to use the combined gas law. P1V1 over T1 equals P2V2 over T2. And now we can solve for our new volume at STP. So P1V1 times T2 over P2T1. All right, so our original pressure is the pressure of our dry gas. So 82.04, that's the worst 8 in the world, kilopascal. And the original volume, they said, was a 500 milliliter container. And the original temperature, they were nice enough to give it to us in Kelvin, but if they gave it to us in Celsius, then we'd have to convert it to Kelvin. The new pressure is STP, standard pressure, which is 1 atmosphere, which is the same as 101.325 kilopascal. And the new wow, I messed this up. T2 is not 292 K. T2 is STP, which is 0 Celsius, which is 273 K. I'm sorry, that's STP for T2. My bad. And then our original temperature was 292. All right, so now we have this set up. We can solve for V2. I'm sorry, we can calculate this for V2, 82.04 times 500 times 273 divided by 101.325 divided by 292, and I get 378 milliliters. Okay. Last problem, I'm just going to craft off the top of my head. It's an initial final state problem. So suppose I gave you this data and I said that we are starting with a sample, and let's say the initial conditions is we have a pressure of 765 millimeters of mercury. We have a container volume of 500 milliliters. And we have at a temperature of 295 Kelvin. And let's say we have moles of carbon dioxide. We have a mixture of carbon dioxide and a mixture of water. And let's say the moles, now let's just say we have a sample of carbon dioxide. Well, I'm not making this too complicated. We have a sample of carbon dioxide, and instead of moles of carbon dioxide, let's say they give us, we have 100 grams of carbon dioxide. And then we're going to change things. Final conditions. We're going to change the number of moles of carbon dioxide. And what we're going to do is we're going to take this container and we're going to add 50 grams of carbon dioxide to it. So we start off with 100 grams and we're going to add 50 grams of carbon dioxide. Now the container, let's say it's a glass jar or something, we're going to keep at 500 milliliters. And the temperature, let's say we're running it in the lab and the temperature of the lab stays at 295 K. I want to know, what is the new pressure? Okay, so we have to say, well, what's changing here? What's changing is we are changing the moles of carbon dioxide. I'm taking 100 grams of carbon dioxide and we're going to add another 50 grams of carbon dioxide. And our volume of our container stays the same. The temperature of the room stays the same. But we're going to change the pressure. So pressure's changing and moles are changing. So this is a Gay-Lussac's law. P1 over N1 is equal to P2 over N2. And they want us to solve for P2, new pressure. So it's P1 times N2 over N1. But they weren't nice enough to give us the moles, so we're going to have to convert to get the moles. We start off with 100 grams of carbon dioxide. We look up the mass of carbon dioxide, and we convert it to moles of carbon dioxide. So we have 100 divided by 44.007, and we get 2.27 moles. 4 sig figs, I'm sorry, 2.272 moles of carbon dioxide. Get rid of this little line, and there we go. 2.272 moles carbon dioxide. And then when we change the conditions, we're adding another 50 grams. So that's going to be 150 grams total. Let's convert that to moles. Now, if they give you the moles, you don't have to do all this conversion, of course. All right, so let's do 150 divided by 44.007. And we get 3.408. All right, so now I can substitute in. So let's copy and paste my little formula. All right. So now what values did we get? All right, our initial pressure was, well, let's look. Initial pressure was 765 millimeters of mercury. And number of moles, we end up with adding 50 grams, so we wind up with 3.408 moles total. And the original amount of moles for 100 grams was only 2.272. All right, so now we're set up. 765 times 3.408 divided by 2.272, you get a really big number. That may be right. I think I hit the wrong button here, so let me try this again. 765 times 3.408 divided by 2.272, and I get, all right, that's correct. 4 sig figs, so 1,148 millimeters of mercury. All right, so I just wanted to show you those 3 type of problems, especially this last one on the initial and final state, because on the practice tests, I'm not able to put in all the different types of combinations, and it's just not time for that in normal class setting to be able to do all that. But I wanted you to see an example involving Gay-Lussac. All right, let's take a look at what we need to do for the test. All right, so here's the thing I posted. It's pretty self-explanatory. I just want to make sure that we're on the same page with this. As far as STP conditions, then yeah, chapter 18 and 19, we're doing 18. But you have to know STP because they're just going to use the term and they think you know what the values are. So know what it is and also know what the actual values are. That the temperature is 273 K and the pressure is 1 atmosphere. Explain the concepts of ideal gases versus ideal gases. All right, that's a chapter 19 topic, but I like to put it on the chapter 18 test because the chapter 19 test is a lot of calculations, a lot of stoichiometry, and I want to keep the tests relatively the same size and scope. So 3 things that you have to know. First of all, what are the properties of ideal gases? What are the property of real gases? Second, you know that there are 2 conditions where we get deviations, and that's going to be high pressure and low temperature, but also you have to be able to explain the physics behind it, that at high pressure, now you have a lot of Coulombic attraction because during compression, you're reducing the distance between the charges. So now you have a lot of force, a lot of attractive force. And with low temperature, you don't have enough thermal energy, enough 1/2 mv squared, in order to be able to keep these things in a straight line path. In other words, they can't do the work necessary to avoid curving towards each other. As far as the relationships for number 3 on inverse versus direct, the graphing, all that stuff comes up again in this test. Number 4, you may have to convert units. I'm going to be taking the questions from a test bank. I generally try to avoid having you convert units at the end of a problem because I think it's a waste of time, but they may not. Converting Celsius to Kelvin. In my examples, again, to save time, I gave you Kelvin temperature, but we use thermometers in the lab, and you're more likely to get a Celsius temperature. Make sure you convert that to Kelvin before you do any calculations in this chapter. Number 6, what is diffusion and what is Graham's law? So conceptual understanding of Graham's law. Number 8, initial and final state problems. We just went over. And all of the 3 different types of Dalton's law in number 9, those will be on the test, as well as the Graham's law. 1, what are the velocities, the ratio of the velocities, how much faster does one diffuse versus the other, and 2, how much time does it take for it to diffuse. The rest of this stuff is on the Chapter 19 test. You can, of course, have your formula sheet with you for taking the test. As far as the practice problems go, there are lots of worksheets I attached to the notes that I posted on Edmodo. So you certainly can go through those worksheets and try those problems. I also attached the answer key. All right, so good luck. Really nice job on the last test, by the way, and I appreciate all the hard work you're doing. So if you have any questions, please feel free to email me. Thanks a lot.